Okay, so we'll start. Good evening. So in the last week, we studied about the different types of gas tungsten arc welding, which are non-consumable arc welding, known as the non-consumable arc welding also. Today, we will study about the consumable welding processes. So, what is the advantage of the consumable welding processes over the non-consumable gas tungsten arc welding is this: the heat input. The heat input is higher in consumable welding process while it is less in the gas tungsten arc welding. So how the heat input determines the efficiency of the welding, the non-consumable and consumable welding process. So we will start. So the gas tungsten arc welding, which is a non-consumable welding process, has a low heat efficiency, and the other welding processes means consumable welding processes like shielded metal arc welding, gas metal arc welding, friction stir, uh, plug core arc welding, and the submerged arc welding. So this has high heat efficiency. So how this has the heat efficiency plays the role in defining the efficiency of this non-consumable and consumable welding process is this: that we know that the heat comes from the arc and the electrodes. So if we see that the in non-consumable, the electrode is negative. So the only heat comes means in the non-consumable arc. So there are two heats means heated anode and heated cathode. So for the non-consumable gas tungsten arc welding, only Q anode is present, and Q anode cathode is absent because the cathode is non-consumable. So there is no heat at the anode contributing from the cathode. And while the consumable welding processes have the heat, total heat as the Q anode plus Q cathode. So because of this addition, the heat available for the welding process is higher in consumable welding processes. So that's why it has the high heat efficiency. So what is the heat efficiency? If we write the equation for the heat input in the that can no, let's say not H. heat input W can be written as neta P Vi divided S. So here N is neta P is the efficiency. It tells that what is the fraction of heat transferring from the arc to the workpiece. While Vi, we know that V is voltage and I is current, and S is the welding speed. So how can we calculate the heat efficiency for different consumable and non-consumable arc welding processes? So let's start. So for that we have to understand the heat distribution in the arc column uh, and between the cathode and anode. So if we draw the diagram, this is positive and, and electrode. This is the workpiece, negative workpiece. This is the arc. So if we draw the voltage distribution, this is anode. So this region is known as the anode pole zone. Means their electrons are accumulating here and here. And this is called the cathode pole zone. So if we draw the voltage difference, so for the anode pole zone, it is very with less rate. And so this is the pattern of the voltage change, change in voltage in the anode pole zone. This called as R2 column. So this is the voltage difference for a arc. So there are three regions: anode pole zone and cathode pole zone, and all three regions have different heat accumulation. So we know that the heat is transferred with by the help of the charge carriers that can be electrons and positive ions. So charge carriers transfer the heat from one point to another. So if we then all three zones have different heat. So if we talk about the amount of heat present in the hole zone, the heat present in cathode hole zone, this written as the QC. So the formula for this is the VCI plus CC V column I minus pi CI minus 3 by 2 K. K is the Boltzmann constant. T column minus TC divided by the charge of the electron and I. I is the current. So the VCI is the energy of the energy produced in the cathode pole zone. Energy of cathode zone. VCI is the energy transferred from the arc column to the cathode, and the minus phi c is the work function heat available at the cathode, means energy required to emit the electrons from the cathode. And this minus 3 by 2 k T column minus Tc by E and I is the energy required to raise the temperature of electrons to the arc column temperature. Because as the electrons emit from the cathode, these electrons should attain the temperature of the arc column to transfer to travel from the cathode to anode. And similarly, if we see the amount of heat present in anode hole zone, that can be written as QA. So this is VAI plus CA V column I plus pi AI plus 3 by 2 K T column minus T cathode divided E and I. So here VAI is the energy at the energy generated at the anode. CA V column I is the energy transferred from the arc column to the anode. The phi C is the energy required to generate the ions at the anode, and this 3 by 2 K T column minus Tc by this term is the means this energy is coming from the moving electrons from the cathode to anode. So all these terms are in addition. While in if we see that the this amount of heat present in cathode pole zone has negative terms. So from the equation only we can assume that the heat available at the anode pole zone is higher than the cathode pole zone. So as the heat is higher for means QA is greater than QC, so the temperature of the anode will also be greater than the cathode. So here uh, cathode is the workpiece and TA is the electrode. So the electrode temperature will be, so the heat available at the electrode will be very high. So it will lead to the higher melting and higher deposition at the workpiece. Means the amount of molten weld metal will be higher because of the heat present at the anode pole zone. So if we talk about the different types of means different difference in the, so now we can write NP is the total energy transferred to the workpiece. So for a non-consumable electrode, where the DC current is used and electrode is positive, so the heat efficiency will can be written as QC divided by VI into 100%. VI is the total heat available. For the second case, where the non-consumable electrode is present and the polarity is different, DCEN means electrode is negative. So the heat efficiency can be written as QA divided by VI into 100%. So for a non-consumable electrode, where electrode is negative, the QA term comes in the heat efficiency formula. So from this equation, we can say that the heat available for a negative electrode is higher than the positive electrode. Next, if we talk about non-consumable electrode and AC current, this is for DC and this is for AC. So NP is written as QC plus QA because in alternating current both electrodes will provide energy, divided by 2 VI I. So this is the average of heat available at the cathode and anode uh, of the percent, 100%. And the next case is the for consumable electrode. Where the both in case of both DC and AC. So the heat efficiency can be written as QC plus QA divided VI into 100%. So if we compare these two equations, so this is the average, but this is just the addition. So the heat efficiency of the consumable electrode in both DC and AC currents will be highest for all cases in of the non-consumable electrode. So this is the most efficient. And as the here it is consumable electrode means the polarity will be electropositive. Good evening, Shobna Priya. Are you able to hear me? Okay, let me continue. So I was talking about the heat transfer efficiency in the non-consumable and consumable arc welding. So the heat transfer efficiency can be written for the DCEP polarity for non-consumable. It is QC divided VI into 100%. So VI is the total heat and QC is the heat generated at the cathode. So, and for the second case, in the non-consumable electrode DCEN, the heat efficiency is written as the Q divided by VI into 100%. So we can see that the for the electrode negative case, the heat efficiency is higher than the uh, electrode positive DCEP. For a non-consumable electrode where AC current is supplied, heat efficiency can be written as QC plus QA divided by 2 into VI. So this is higher than the direct current non-consumable electrode. For the in the last case, for for consumable electrode, in both where both DC and AC is supplied, so the heat efficiency can be written as QC plus QA divided by VI into 100%. So by seeing these terms, we can see that the highest efficiency is for the consumable electrode. So and also the consumable electrode, the polarity is electrode positive. So if we talk about the heat efficiency for different processes, so for gas tungsten arc welding, DCEL, it is 50 to 80%. For gas tungsten arc welding, DCEP, it is 40 to 70%. For plasma arc welding, it is 50 to 80. For shielded metal arc welding, it is 70 to 90. For gas metal arc welding, it is 60 to 90. And for submerged arc welding, the heat efficiency is 90 to 100%. Means the highest heat transfer efficiency is for the submerged arc welding. So now if we want to calculate the melting rate of the consumable electrode or wires, so so this can the melting rate represented by M can be written as the melting rate is the mass of electrode material melted and transferred from the electrode. To the workpiece per unit volume. So the equation for this can be written as the Q QC or QA minus H and minus TD minus TM to CP. So QC or QA we know is the heat efficiency of cathode or anode. H is the, or sorry, one more term is the QJ. So H is the latent heat. This is the heat required to increase droplet temperature. And Qj is the Joule heating between the cathodes. So the Joule heating QC and QA we know. Qj can be written as the I square R, and R we can write as the rho L divided pi R square. Rho is the resistivity. So if we write equation for QA, so this is VA plus CAI and so QA is this, QA can be written as this. So if we put these terms in the melting rate equation, the melting rate can be written as AI plus B L I square divided pi R square. Here A can be written as VA plus CAB column plus pi C plus 3 by 2 KT column minus TC divided E, and the whole term is divided by H plus TD minus PM into CP. And B can be written as resistivity divided H plus TD minus TM CP. So here if we note that the phi C is the work function of the anode, phi is constant, voltage is constant, latent heat is constant, and heat capacity of the material is constant. So this term, so A and B will be A and B are constants. So only variable in the melting rate is the current, and length and the radius of the wire. So variables of melting rate is R. L is the stick out length of the wire, I is the current, and R is the diameter of the wire. So if we write, so this is the electrode and the wire coming out from the electrode is, so that length is called as the stick out length. And this term we require for to increase the temperature of the droplet to to release from for the detachment of the droplet and droplet. This is required because as the material melts, the droplet forms, and the droplet will only detach from the electrode when the droplet temperature will be higher than the so means we have to superheat the uh, superheat the droplet for a higher temperature to release it. So for this condition, this melting rate equation, and if the wire diameter is also fixed, so we have only two variables, stick out length and current. So we can vary the our welding process heat input by melting rate by this varying these two inputs, means current and the stick out length. So if we see from the equation, it is the melting rate is uh, directly proportional to the current and stick out length. So as the current and stick out length increases, melting rate also increases. While for a higher diameter wire, it is inversely proportional. So as the diameter of the wire increases, melting rate decreases. So here we can see these two graphs for melting rate of a consumable wire. So here this plot is given for the burn off rate, means melting versus current for a different stick out length. So for a 5 extension, this curve is followed, and this A is for the highest stick out length. So for a 20 extension, the burn off rate, means melting rate, is has a higher slope as compared to the other stick out lengths. So from if we draw a straight line, so if we draw a straight line from this is for a for a current value. So the burn off rate or melting rate for a 20 stick out length is highest. So the stick out length as the stick out length increases, the burn off rate or melting rate increases for that consumable wire. And the second graph is of the uh, wire feed speed versus the current for a different wire diameters. So as we know that the melting rate is inversely proportional to the diameter. So as the wire diameter increases, the wire feed speed wire feed speed is also related to the melting rate. So this will also uh, increase with the decreasing of the wire diameter. So the for the smallest dia, 0.8 mm, the wire feed speed increases much higher with increase in current. So this is for 0.8, this is for 1.2, this is for 1.6 mm. So for a small wire diameter, the wire feed speed is the highest. And so Brijmohan Sharma ji, are you able to hear my voice?
Yes, ma'am. I'm able to hear, but just now I have joined,
Okay.
so I don't have clear-cut idea about which process you are talking about.
Yeah.
Is it GMAW?
Yes, it is GMAW. I'm discussing about the melting rate in the of the consumable wire in the gas metal arc welding, or the means where consumable welding process. So
Okay, okay, ma'am.
I will
Please.
just go through the previous pages. So here I calculated the melting rate. So melting rate is can be written as the mass of electrode material melted and transferred from the electrode to the workpiece per unit volume. So this can be written as the uh, QC heat of the uh, this QA is the heat presented at the cathode or anode minus H is the latent heat minus the TD minus TM CP. So this term is for the heat required to increase the droplet temperature, and plus QJ. So this is QJ is the joule taken to melt the electrode.
Okay, ma'am. Just to know, ma'am,
Yes,
this expression
yes.
is it taken from some textbook, or I mean from where it is derived?
Yeah, it is taken from the textbook only, because have you gone through the lectures of the week six?
No, ma'am, not yet. I haven't go through it. Yes.
Okay, so I'm discuss means in the last week we discussed about the different types of gas tungsten arc welding. So that
Uh-huh.
gas tungsten arc welding has the lower heat efficiency, because
Yes, ma'am.
uh, the heat available because and the is less, means for I will just go through this. So for the gas tungsten arc welding is non-consumable process. So this has the low heat efficiency. So if we say this Q is the heat for the, so there are two types of means heat uh, uh, three heat regions. So this is the
Mhm.
arc column. So here this is the positive electrode and this is the negative workpiece. So in the
Okay.
previous lectures we studied that the uh, for region, so at the positive electrode, electrons will accumulate at this region. So this is
Uh-huh.
called as the anode pole region, and the for at the workpiece, positive ions accumulate. So this is known as the cathode pole zone, and the
Mm.
in between region is called as the arc column. So all these three regions have so this is the voltage variation in all three regions. So for the anode pole zone and cathode pole zone, the arc the voltage changes gradually, and the arc in the arc column the voltage increases uh, abruptly. So the because of this voltage difference, the heat generated at these three
Both this
regions
side.
will also be different.
Okay, okay.
And we know that the heat is transferred by charge carriers.
J.
So if we talk about that, how much heat is present at the cathode or anode. So if we talk about the cathode heat, amount of heat present in cathode fold zone, so this can be
Mhm.
written as the this expression VCI plus CC V column I minus phi C I minus 3 by 2 K T column minus TC divided by E. E is the charge of the electron
Electron. Okay.
and multiplied by I. So first
Uh-huh.
term is the energy of the cathode fold zone,
Okay.
and this term is the heat transferred to the cathode by the arc column,
Mm-hmm.
and this term is the uh, work function or the heat required to generate the electrons at the cathode, and this term is the heat required to increase the temperature of the generated electrons to the arc column, to the arc column temperature. Means
Okay.
here we can see.
Just ma'am, I would like to interrupt you in between.
Yes, yes.
Can you please suggest any other than this lectures delivered by sir? Can you suggest any textbook so that I can refer it
Yeah, the textbooks are
for this type of
shared in
thing?
the lectures also, so you can go
Uh,
through these. Means four textbooks are shared. So
okay, so
if you
in
go
the
through the
lecture,
first lecture of the week one
okay.
series, so in the text book link or the text textbook name is given, so you can
Mm-hmm.
download from the those textbooks.
Surely, ma'am, I will.
Okay,
Yeah,
so
and then.
in this term, the two terms are negative. Means the uh, this heat we have to give to generate the electrons. Means phi c is the work function of the cathode material,
Mm,
and current is the current we supply from the power source. So all the terms has the uh, current current term, and this is the term required to increase temperature of electrons.
record increase the temperature of electrons.
Electrons to the arc column to temperature of the arc column. Means the uh, electrons are first generated at the cathode, and they have to transfer, means they have to travel from the cathode to anode. So first they have to attain the temperature of the arc column, then only they will be able to travel from the cathode to anode. So this
Mm-hmm.
heat will be consumed in the that process.
J.
Means the total heat will have some two terms are negative and two terms are positive. And if now we see the heat present at the anode, means anode fault zone.
Mm-hmm.
So this also has terms similar to the cathode region, but in the positive, uh, and means these terms are adding to this heat generated. So VAI is the heat generated at the anode, because the as we supply the current, so some heat will all will already present at the anode because
Mm-hmm.
of the voltage difference and current supplied,
Yes, ma'am.
and this term is the heat transferred from the arc column to the anode. So this is the fraction, uh, means the whole means the uh, not total heat will transfer from the arc column to the anode. Only a fraction will contribute. So this is the fraction constant.
CA. C is fraction constant. Huh?
V column I is the heat of the arc column.
Okay.
So some fraction of the heat from the arc column will transfer to the anode. And
Okay. Next is work function multiplied by current.
yes, no
Third term.
power. V and I is the heat. We write this power term as the VI. So
VI,
this
yes,
is
ma'am.
the heat.
Hmm.
And the next term phi A is the heat
Work function.
required to generate ions at the anode.
Hmm.
And this next term is the heat required to increase the temperature of the ions at the
Okay.
anode. So
So not
this
electron
means
process.
the here it will be positive ions. So
Okay.
positive
Okay.
ions will also travel from the anode to cathode. So they also this is electrons only.
Cathode to anode. Huh?
The electrons are electrons coming from the cathode will really transfer the energy to the anode region.
Anode. Yes, ma'am.
So this is the same term, means the heat required to increase the temperature of electrons to the arc column
The
temperature.
previous one.
Yes,
But there it was minus. Here it will be
yeah,
plus,
all
right?
terms are positive. So we can see that the heat available at the anode is higher than the
Greater
cathode.
than QC.
So
Yes, ma'am.
from because this heat is higher for the anode, so and so therefore we can say that the temperature of the anode will be uh, higher as the cathode. And
Hmm.
here sorry, Ta is means these are the we are talking about the anode full zone and cathode full zone. So the anode full zone, which is electrode, will have the higher heat and high temperature. So that's why
Okay.
the heat means
Electrode will melt
heat
out.
will so yes, since the heat is higher for electrode, so the electrode will melt easily.
Hmm.
So the we know as the heat in, if we write the term of the heat input is the neta p vi divided by speed. So this vi is the power, neta p is the heat efficiency, and
Hmm.
s is the speed of the means welding speed.
Welding speed, yes, yes.
So NP is written as the total energy transferred to the workpiece. So if we talk about the different processes, means for the non-consumable electrode, where the polarity is the current supplied is DC and electrode is positive. So
Positive.
the this energy means the neta p value term can be written as the QC divided VI into 100%. So from the previous equations, we saw that the QC is less than the QA. So the heat transfer efficiency for this non-consumable electrode in DC-EP polarity will be less. If the polarity is changed to electrode negative, so the heat heat efficiency can be written as the QA divided VI into 100%. And we know that the QA is high as the QC.
Hmm.
So the
QC.
heat efficiency of this DCEN non-consumable electrode will be higher than the this previous case. And further, if we talk about the non-consumable electrode, where
Now, what
AC,
is this? Sorry, but what is this Na and NP?
sorry, I will
This is efficiency. First and second one.
yeah, neta P is the heat efficiency. This
Okay.
are you are
So,
asking about this now?
hmm.
Yeah, this is the we write
This
this
total energy
this is
transfer
the
to
heat
the.
efficiency of the process.
Okay. No,
Means
but what is the point you would like to
I just want to
go from point number one and two, ma'am?
one and two.
Non-consumable electrode DCEP. So,
Non-consumable electrode DCEN means when the polarity change from the positive to negative of the
mm,
electrode, so the for a negative polarity of the electrode, the heat efficiency will be high for the non-consumable DCEN as compared to
so
the
this will be preferred one, or what
no,
does it mean?
means we use the different according to the
Polarity.
requirement for a
Okay,
different
okay.
process.
So if I want melting right high of electrode, then I should go for DCEN.
Yes,
Is it so?
in the non-consumable electrode.
Okay. So in GTAWR.
Yes, if this two case means these first three cases are for this third case is also for non-consumable. So the
Okay.
three cases are for gas tungsten arc welding where non-consumable electrode is used.
Mm-hmm.
So for these cases, where different means DC or AC current is applied, and the polarity of the electrode will contribute to the different amount of heat efficiency.
So I just want to know if I am having a workpiece of a say for 1 mm or 2 mm thickness.
Yes,
Then in that case, I think to for this burn through case
yes,
to avoid this burn through case, I should go for DCEP.
yes. If we want the less heat input for our process, so we can go the this polarity with the
And for
aluminum fuse.
aluminum welding, which
So
uh,
in aluminium welding, we because aluminum has the temperature of 660 melting temperature 660 degrees Celsius. So the
yes, ma'am.
heat input will only depend on the thickness of the workpiece.
Uh-huh. Actually, there is one aluminum oxide layer which is having very high melting
Yes.
point.
So for that we use the AC. So in AC we the polarity change after every half cycle, na? So for a
Mhm.
for positive cycle, uh, yeah, so for positive cycle, the electrode will be positive and the workpiece will be negative. So electrons will transfer from the workpiece to the electrode, and the electrons, no, the positive ions will travel from the, because in the DCEP case, the electrode is positive, so the
Mm.
positive ions will come from the electrode to the workpiece. So those positive ions will strike to the workpiece and clean the that aluminum oxide layer. So
But at the same time, electron will leave the surface of the
workpiece,
workpiece, right?
yeah, so that will be has less efficiency. And in for the next half cycle where the electrode will be negative, so electrons are coming from the electrode to the workpiece. So the electrons have means they are light and they can attain a very high temperature, so they are able to transfer the heat means more efficiently. So as the electrons are moving from the electrode to workpiece, so they will strike on the workpiece, increase the temperature of the workpiece, and leading to the melting. So for aluminium, we use AC current.
Okay, ma'am.
So for the first cycle, the workpiece will get cleaned, and for the second cycle, the welding will done.
Okay, okay. Yes, ma'am. I got your point now.
Okay, so
Mhm.
for this non-consumable where AC current is supplied, the heat efficiency term can be written as the QC plus QA divided 2VI. So this is the average of the QC plus QA into 100%. So this term is also has higher efficiency than the both previous cases where the DC current is supplied. So for the AC current is supplied, the heat efficiency will increase. And in the last case, we talk about the consumable electrode where the both AC and AC or DC current is supplied. So the heat efficiency can be written as the QC plus QA divided VI into 100%. So in this term, the QC and QA are added. So the heat efficiency will be highest for this case. So this is for consumable electrode welding.
Yes, ma'am.
So if we write the different heat efficiency for different welding process, so for the gas tungsten arc welding DCEN polarity, the heat efficiency is 50 to 80%. For the DCEP case, it is 40 to 70%. And if we talk about the plasma arc welding, the heat efficiency is 50 to 80%. And so these are the non-consumable process, and these three are the consumable electrode process. Means shielded metal arc welding, gas metal arc welding, and submerged arc welding. So both all three welding processes will have higher heat efficiency as compared to the non-consumable welding process. And the highest heat efficiency is observed for the submerged arc welding, because the heat is protected by the surrounding uh, flux granules. So the 100% heat generated will uh, consumed by the welding process in the submerged arc welding. So up to this point is clear.
Yes, ma'am.
Okay. So next we will go to the melting rate of the consumable electrode wire. So this can be written as the melting rate is the mass of electrode material melted and transformed from the electrode to the workpiece per unit volume. So this can be written as the uh, QC or QA, I mean, depending on the polarity of the electrode, minus H minus TD minus TM multiplied by CP and the QJ. So QC and QA, we know these are the heat available at the cathode or anode pole zone, and H is the latent heat of the that electrode material, and the this next term is the heat required to increase the droplet temperature. Means as the electrode melt, the molten droplet um will only means fall when the heat is higher, means the temperature of the droplet will be higher than the melting temperature of the material. Then only the droplet will detach from the electrode. And the QJ term is the joule heating uh, available for the electrode and workpiece. So yes. So this is the QJ, means joule heating can be we know that the joule heating formula is given as the I square R power, and here I.
Sometimes T is also involved. I mean, what is the difference? I square R and then T is time. That is also mentioned sometime. I don't know.
This is the heat generated, and time is the, yeah.
So
Then
time will be included in this I square R.
no, in this term we don't. This is the this only the melting rate.
Okay. It is rate basically per unit time.
Yes. So this is
Okay.
the mass available, means the mass of the electrode material melted and transformed from the electrode to the workpiece. I will only come when the travel speed is included.
Okay.
So when the travel speed is included, then the time at the electrode is in contact with the workpiece, then only the time will come. So, but in this for melting rate calculation, we don't include the time. So this I square R, and R can be written as the rho L divided by R square, where rho is the resistivity of the electrode, and this term is for the QA, means
Okay.
equal zone. So
That we have discussed earlier, right, ma'am?
yes.
Mm.
So this is just so the melting rate can be written as the AI plus B Li square divided by R square. So here for in this is the equation for the final melting rate. So here A and B are constants. So A can be written as the uh, this is phi A. So A can be written as the VA plus this means only the I term is excluded from this, and this is divided by H plus TD minus TM. It is CP.
Mm. Okay, ma'am.
CP. And B can be written as rho divided by same term, this H plus TD minus TM CP, because these terms are negative, so so these terms are coming in the denominator. So from the melting rate equation, we know that the phi is the work function of the electrode material, V is the voltage, H is the latent heat, and Cp is the specific heat capacity. So these term will always be constant. So the variables available for the melting rate is are the L, I, and R. So here L is known as the stick out length of the electrode, means this is the electrode and the wire coming out from this electrode. So this length is known as the capital L stick out length, and R is the wire diameter. So if we fix the wire
I
diameter
think
also,
R is wire radius, no?
oh,
Or
radius.
wire diameter,
Yeah, if
no?
radius.
Radius only. Okay,
So
okay.
generally we use the fixed radius wire only.
Hmm,
And
hmm.
wire radius is also fixed. So we have only two variables, means the stick out length and the current. So the
Hmm.
melting rate is directly proportional to the current and the stick out length, and it is inversely proportional to the wire radius.
Hmm.
As the current and stick out length is going increased, so the melting rate will also increase. And if the wire diameter is increased, then the melting rate will decrease.
Okay.
So next, so these
Oh,
two graphs are explained. So first graph is for the melting rate versus current for different stick out length, and the second graph is for wire feed speed versus current for different wire radius or wire diameter. So for the first graph, So this graph is plotted for a 1.2 mm plain carbon steel uh, in argon plus 5% CO2 atmosphere.
Mm-hmm.
So for for a current amount around 250, if we draw a straight line, so these A, B, and C are the different stick out length. Means the stick out length is the uh, larger for the A. So A has the 20 mm, B 10, and C is 5. So for the higher stick out length, we have the highest melting rate achieved for that same current value.
Okay.
And the second graph, this first line is 4.8 mm wire diameter. Second line is for 1.2 mm wire diameter. The third for 1.6 mm. So for the smallest wire radius, the means the wire feed is so we it is uh, assume that the wire feed is generally equal to the melting rate.
Mm.
So the wire feed speed is highest for the uh, smallest wire diameter. So for this, the melting rate will also be higher.
Okay. So, ma'am, if I am having say for 1.6 mm wire diameter,
Yes,
uh, but I want the same melting rate.
same melting rate. Then you have to
Yeah.
increase the current.
Then only the option I am having is to increase the current only.
Yeah,
No?
current and stick out
No.
length also.
And what if I increase the voltage?
No, voltage will not contribute in increasing the melting rate because if the voltage increases, the arc stability will go down. So for a better
So
welding
stepping will
process,
be
we need stable arc. So for we means we keep the voltage always lower in the 10 to 30 volt range,
okay. Okay.
and the
And
current is yeah.
if I will increase, then scattering will be more. Is it so?
Yeah, spattering will be will be high, and the means the arc will not be stable.
I mean, I'm not able to exactly understand what is the stability of arc basically.
Arc stability is the means steady steady means heat generation is steady.
By seeing that arc, can we utilize it as an stable arc or it is an unstable arc? How we will distinguish between these two, stable or an unstable arc?
Because in the unstable arc, the arc is for only a certain means for some period the arc will be very high, and for some period the arc will be very low. Means if we talk means arc intensity will be low.
Okay,
So
okay.
the as the voltage increases, the arc intensity will change abruptly
Hmm.
in the welding. So it depends on the arc intensity. So the in between the arc intensity can go very low or very high. So in the low arc intensity, we will not be able to weld properly, and for high intensity, the means we can get a shock also.
Yes, ma'am,
Means
I
the
got you.
in a stable arc, we can see that the lightning of the in the clouds. So that
Uh-huh.
is
Yes.
the unstable arc. So that is
Uh,
only for a very small time,
uh,
and for and of a very high intensity.
yes, ma'am.
So this is not required for a good welding process.
Hmm.
So for
Yes, ma'am.
we need the constant intensity of the arc for higher
So
lightning.
basically, ultimately, ma'am, the bead will be, I mean, not continuous
Yeah, bead
if
will
there
not
is unstable.
continuous.
Huh?
Yes, yes, sure.
That is okay. Okay.
Hmm. So
Yes.
the when the arc will not be stable, so the we will not get the good welding bead. Means spattering will be high, and we have also at the some position high deposition, at some position we will have undercuts or a lack of fusion.
Yes. Yes, ma'am. So, is there any particular criteria that this bid is acceptable, this is not acceptable? I
Means
mean, is there any or any standard? I mean, to refer so that we can find out that yes, this bid is acceptable for industry or something like that.
means
Yes,
welding bead,
welding bid.
so that should be uniform. Means if we have these two work pieces, so for a given length, means the weld width should be uniform. For any process we will require this. So this is the first requirement, means the this is the welding bead, so it should be uniform so that we can get the good mechanical properties of that welding joint.
Ma'am, is there any standard to refer
No, this
ASMA or some
mm,
is- Indian standard for this type of thing?
I don't know the exact standard, but this depends on the different process. Means for a uh, depending on the different welding requirement, we can change the welding bead geometry also. So means for all welding processes, we require different weld bead geometry.
Okay, okay, ma'am.
Okay. So the we use the voltage in the this 10 to 30 range, and current can increase according to the heat requirement.
Hmm. Yes, ma'am.
Okay. So next we will study that we we talked about the melting rate. Now the how the that molten wire will transfer to the workpiece. Means the molten metal should also have some criteria to transfer from the electrode to the workpiece, then only that the welding will occur. So for that, so what are the different forces that lead to the uh, easy transfer of the molten this molten droplet to the workpiece? Means this is the molten droplet created at the electrode, so it should transfer to the workpiece. So there are different types of forces which determine the droplet transfer. So first force is the gravitational force, Fg. Second force is the aerodynamic force, Fd. Third is the electromagnetic forces in the arc. So the electromagnetic force comes from the arc, in electric field in the arc. This is also mm, known as the Lorentz force. FEM. Fourth force is the vapor jet forces. F R no, please. F V. The fifth force is the surface tension of the droplet. FST. So now we will discuss the contribution of these five forces one by one. So generally the equation means balancing equation between these forces is written as the Fg plus Fem plus Fd is equals to Fb plus Fst. Means here as we know that the gravitational force will only act downwards, so as the droplet weight is achieved to a level that the electrode cannot hold it, so the because of that gravitational force the droplet will uh, drop down to the workpiece. So this is for the Fg, means this will the gravitational force assist the transfer of the droplet to the workpiece. The electromagnetic force comes from the charge carriers, means as the we know that there is a sharp edge between the droplet and the electrode. So for this sharp edge, the area is less area available. So the electrons or ions accumulated at this position will have less area, and because of the less area, they are compressed for compressed at one near to each other. So and the those charge carriers at a time at one time will repel each other by a force, because we know that means same charge carriers repel each other. So because of that repulsion force, the force will also apply on the droplet, so that will lead to the drop down of this droplet. So this so the force generating in the uh, constriction of the charge carriers is known as the Lorentz force. So Lorentz force will also help in transferring the droplet to the workpiece. So this and the drag force comes from the shielding gas environment created. Means aerodynamic force means the shielding gas only is also going from the electrode to the workpiece or environment. So that aerodynamic force created by the shielding gas will also assist the transfer of this droplet. So the all these three forces are added for the left hand side, and these two forces, which are the vapor jet forces and the surface tension, will uh, will oppose the transfer of the droplet from the electrode. Means
Hmm.
vapor jet forces are created by the metal vapor generated from the workpiece. Means as the some workpiece area get melted, and that molten metal uh, after reaching some higher temperature, they converted into the metal vapor. Means the molten metal will vaporize, that will create a upward force for the uh, droplet.
Ma'am, is the spattering is due to this vapor jet forces?
Yes, means the all we will study here in means after talking about this. So, yeah, so for this also this also lead to the sputtering and some more criteria lead to the sputtering. So this vapor pressure is the metal vapor generated in the arc column, and because they means the oppose the uh, drop down of this droplet. So and the surface tension. As the droplet forms and it will uh, it wants to drop down, so it is first it is attached to the electrode, and it as it releases from the electrode, so a small surface area will increase for this droplet. So the surface tension will not allow the droplet to drop down because the surface area will increase, that leading to surface tension. So that's why to minimize the surface tension, this force will not allow the droplet to drop down. So
Yes, ma'am.
that's why it comes in the right hand side.
Right.
So when these three forces are greater than these F, means vapor jet forces or surface tension, then only
Question.
the droplet will come to the workpiece.
Okay, ma'am.
So we will discuss these forces one by one.
Ma'am, I'm sorry to interrupt you.
Yes.
Actually, here there is a power cut at my side,
Okay.
and my actually data is going out.
Okay. Then
So, so ma'am, just I would like to put a request
yes.
that if I'm having any doubt,
Hmm.
may I have your email
Mail.
ID so that
Yes. Yes. I can write it. My mail ID is symbol math 016 @gmail.com. This is my mail ID.
so ma'am, are you also a research scholar?
Yeah, I'm a PhD scholar in third year,
From which institute, ma'am?
IIT Delhi.
Acha, you are from IIT Delhi, but this course is, I think, from IIT
Yeah,
Chennai, right? Ma'am?
yeah. So I'm NPTL means PMRF TA. All need to do this online TA or outside TA. So I got this NPTL TA and the course will. So we can choose any course from the all IITs.
Okay, okay. So, ma'am, your research is area is also the same in welding or
I'm
something?
doing my research area is on the wire arc additive manufacturing.
Acha, WAM, huh? WAM.
Yeah. So you're doing PhD or you're,
Yes, yes, ma'am. I'm research scholar at MNIT Jaipur.
okay, okay, I'm an IT nice.
Yes, ma'am.
So in mechanical
So,
or materials?
ma'am, mechanical and welding itself.
Okay, okay.
There is as Arvindan sir is also there, I think.
Yeah, yeah, yes, Arvind sir. He is my external super means external examiner in the SRC committee.
Acha, acha, acha. Okay, ma'am.
Yeah, so you can post the any or have you registered on the course portal? So there is one discussion forum, so you can post the
Discussion forum is
questions
also there. Yes,
there
yes, ma'am.
also, and
But
we
actually, there is I can only discuss about say for some welding related questions.
yeah.
But some specific questions, say for here during my research, if it is there, then I would like to request you that I can, I mean, uh,
Yeah, you
take
can mail on this.
some guidance from your side as well.
Yeah, this is my mail ID, so you can.
Yeah, ma'am, I will definitely reach if there is any difficulty. I'm just.
Okay.
So thank you so much, ma'am.
So
Hmm.
you are leaving the meeting.
Yes, ma'am, I have to leave actually because there is no power. I don't know what happened.
Okay, okay.
I am
Then
I am at MNIT. MNIT now. I am at MNIT now, but I don't know. There
so
is
in
some
which
power
semester
cut
you
due
are?
to.
Hello.
You,
So in which semester you are?
ma'am. Actually, I am in fifth semester right now.
Okay, fifth semester.
Yes, ma'am.
Yeah, me also same. I'm also
So,
in
but
fifth
actually,
semester.
I am part time, ma'am. So,
Okay, okay.
uh,
So
I
you are
there
doing
is.
job somewhere.
Yes, yes, ma'am. I am also assistant professor at SKIT Jaipur.
Okay, okay, nice.
So basically, ma'am, who is your guide there?
My guide is Professor Lakshmi Narayan. I'm in
Lakshmana.
material science department.
Okay, okay, okay.
Okay.
Nice, ma'am. Thank you, ma'am.
Okay, so
Thank you.
I'm recording the lectures up to these
Acha, the
chapters.
recording will be available.
Yeah, recording
The
will be
recording
available at the course site.
at the end of the course.
No, no, you can you will get this recording link in the this week also, means 1 or 2 days later.
Okay, okay, ma'am. Then I
You
will
can go through that
use it.
recording.
Definitely, ma'am.
Okay,
है ना? Okay. Thank you, ma'am. Ma'am, I'm sorry, but please allow me to leave. है ना?
okay, okay, fine. So this image is shown for the balance of forces in a droplet. So this is the electrode, and this is the droplet created, and this is the so the Fd is the aerodynamic force working downwards. The Fg is the gravitational force. This is also working downwards. Fem is the Lorentz force. Will also assist the drop down of this droplet. Only the Fv, which is the vapor force, vapor jet force, and St surface tension force will oppose the transfer of the droplet to the workpiece. So if we discuss the uh, gravitational force, so gravitational force is given as the 4 by 3 pi r cube. This is the droplet diameter radius rho g, and g is written as 9.81 cos theta. Means the gravitational force will only will also be determined by the position of the electrode with the workpiece. So for a theta equals when theta is 90 degree, means this is the electrode and this is workpiece. No, this is in case of this. So theta is 90 degrees for overhang structure, and theta equals equals to 0 degree is for horizontal position. So for the horizontal position, the G will be 9.81. And here RD is the radius of droplet. Rho is the density of food. And G is for a, so for a 1.6 mm wire in argon atmosphere and low current. And the Fg for aluminium metal is 260 and Fg for iron is 600 into 10⁻⁵ Newton. Second is the aerodynamic force. It is also known as the plasma drag force. So the Fd formula is written as the 0.5 pi v square d r square c. So v is the gas velocity, d is density, r droplet radius, and c is the drag coefficient. And Fd is minimum, no, Fd is maximum with a large droplet diameter. And high gas velocity. Third force is the Lorentz force. FEM can be written as mu I square divided by phi ln RE square divided R. So mu is the magnetic permeability. R is the exit radius of current, and capital R is the entry radius. Means this is the R, capital R, and this is the RA. So FEM can be large up to 0.02 I square. So here we can see when will the uh, uh, what will be the droplet shape for a different Lorentz force. So for a low current, the RA is smaller than the capital R, so the droplet will not detach from the electrode. For a high current, where RA is smaller, RA is very greater than the um, capital R, so this will lead to the detachment of the uh, so the size of the droplet will be big. For a case where capital R is greater than the RA, no, for this case where pointer electrode, so this is R, this is RA, so this will lead to the streaming case. And for this case where R, for this proportion of the capital R and RA, the globular so yeah, so this arrow will from this arrow we can identify the easy or easy detachment, means this lead oppose the detachment. This assist high current assists the detachment drop down of the metal droplet. This also assists, and in this case it is the drop down is opposes. So next force is the vapor jet force. So FV can be written as M naught divided dV I J. So here I is the current, J is the current density, dV is the vapor density, and m naught is the total mass vaporized. Per ampere or per unit time. So this force always opposes. So FV always oppose droplet detachment. The final force is the surface tension. So FST is given as 2 pi RW sigma multiplied by a function of RW and C. So here RW is the wire diameter, wire radius, sigma is the surface tension, and this is a function of the wire radius, and the C is the capillary constant. So the surface tension depends on the mode of transfer, and composition of the electrode. Means for different metal electrode, the surface tension will vary. For FS, so FST for aluminium is 300 into 10 raised to power minus 5 Newton, and for iron it is 600 into 10 raised to power minus 5 Newton. So for aluminium it is low, and for iron it is high. So based on these imbalance of these five forces, we have different types of transfer, metal transfer. First is the metal transfer can be divided into two types: free flight or short circuiting. Free flight will further classified into globular, ripple, spray, and jetting spray. So for the globular transfer, so we'll study one by one. First is the globular. For globular transfer, we have large transfer and low transfer rate, low currents and high voltage. So globular transfer has low transfer rate. It is accurate, low current, high voltage. But it depends on shielding gas and composition. So this works for a 1.6 mm dia, aluminum wire with argon shielding. It is 100 ampere and with CO2 shielding. The current required is 200 ampere. For rippled transfer, means the droplet is accumulating at the electrode only, so it will gain this shape. So this is called as the ripple shape. So this ripple transfer will occur at higher currents and here Lorentz force created, force generated. So the ripple shape generate from the Lorentz force, change in the Lorentz force and electromagnetic force. Electromagnetic forces. The third is the projected spray transfer. So this projected spray transfer occurs for increase in current. When current is increased, leading to this lead to decrease in droplet size. Further that lead to increase in frequency. Frequency of drop down. It means small diameter droplets are generating and they are detaching with a higher frequency. So this have the steady stream of droplets. Droplets with the diameter same as wire. Means the droplet diameter is same as the electrode wire. And the current, one point is this is second point. Third point is this. The current at which this transition happens occur is known as spray transition current. So as the current increase means welding rate increases that lead to small droplet and less spatter. So if we uh, understand this graph, this is a drop volume versus current. So with increasing current, the transfer will change from the globular to the projected stress transfer. So for the lower current, the transfer is globular. For a higher current, it is ripple. And this position, this is projected. It becomes projected. So this current is known as the spray current, spray transition current. And the A graph is for the droplet volume and B is for transfer frequency. So with increasing current, the transfer frequency will increase. So at this point of frequency and current, this is known as the spray transition current, SPT. Next is the so this is the projected spray transfer plain carbon steel for a plain carbon steel wire with varying the wire diameter in a different shielding gas atmosphere. So for an increasing amount of CO2 with the spray transition current for a diameter increases with increasing amount of CO2 and with increasing diameter also the spray transition current is increasing with increase in diameter and with increase in CO2 5%, 15% and 20%, the spray transition current is also increasing. Next is the streaming transfer. So this streaming transfer occurs for very high currents at 300 ampere. So in this case, the droplet diameter reduces to a very low level. Means the small droplets will fall for very high with very high frequency. So continuous stream will lead to the streaming transfer. So in this case, the electrode will get tapered and very fine stream of droplets. So this happens because of the as the tapered electrode tip will have high Lorentz force. So because of this high Lorentz force, the frequency of the detachment will also increase. So this streaming transfer also occur in high resistive highly resistive, and small dia wires. So because of this highly resistive and small dia wires, the well-cooled turbulence will be high. So that will alter the weld microstructure. Means in the turbulence, the microstructure will be fine. So this streaming transfer is used for sliding applications. So this is for cladding application, but for a gas metal arc welding process, the current is kept near the spray transition current. So there is one more transfer mode, which is known as the drop spray transfer. So the drop spray transfer is preferred for the gas metal arc welding process. Drop spray means in this case the current is kept in that range that droplets form at circular and will also transfer with a certain frequency. So this is the ideal transfer mode, and it is efficient and clean with a very low splatter and fume levels. Next transfer is the dip or short circuiting transfer. So dip short dip short circuiting transfer works on the principle when the electrode is uh, is mo- um, is moved to the near near to the workpiece and bring in contact. So this is the wire electrode and the arc is generating here, and the wire feed is here wire feed is speed is increased as the wire touches the workpiece, the arc will extinguish. So, and because of the joule heating created at the joint between means at the point of the electrode tip and workpiece, so the joule heating will lead to the melting of the electrode, and the a molten electrode uh, will retracted by will re, means move back for a bit slowly to generate the metal droplet. As the wire move up, that will lead to the generation of the metal droplet and decrease in the um, decrease in the tip area. So that will lead to the high surface tension. And here the force are contributing in the detachment of the droplet is surface tension. And as the further the wire moves up, so that will lead to the detachment of the droplet. So for this dip short circuiting transfer, we have to carefully manage the current and voltage. Means for a certain period when the tip when the so this is for the arc position when the wire speed increased and the wire comes in contact with the workpiece. So at that time arc will goes off and current will decrease to zero. No, this curve is for current and this curve is for voltage. So at that time, voltage will go zero, and at that point, current is also minimum, kept minimum to avoid uh, any um, any accident. Because of this, means we have to keep the current low while coming the while reaching the workpiece. And after that, as the wire retracted again will retracted, so the voltage in current is increasing for the some time, and the arc extinguish will means arc will generate, and for after some time when the wire comes in contact with the workpiece, the current and voltage will as the voltage goes zero, the current will be low. So we deliberately keep wire feed speed higher in this case. So the frequency used in this case is generally 100 Hz. So in this, the advantage of this dip short circuiting transfer is the controlling heat input. Means the heat input can be controlled via via careful manipulation of the current and voltage. So this is generally used for the advanced gas metal arc welding and CMT means cold metal transfer. Why it calls cold metal transfer? Because the droplet temperature here is less in comparison to other methods. Next transfer is the explosive transfer. So explosive transfer is occurs due to uh, gas metal or slag metal reaction inside droplet. means the reaction occurring in the inside the droplet will increase the temperature at that level that the droplet will explode, and the explosion may assist so this transfer is generally used in flux core arc welding, but it also causes arc instability in gas metal arc welding. So the explosive transfer is only used in flux core arc welding. So the application is in the spray or coating. Next is the rotating transfer, means the a molten droplet will rotate is rotated with the electromagnetic forces in the arc. So this happens at a very high current. So very high current lead to rotation of streaming droplets. So this transfer is usually undesirable, but used in surfacing applications. So they so this is all for today. We will discuss in next lectures about the shielded metal arc welding, flux core arc welding. So thank you.